All right, so our last section of chapter 9, we're going to deal with the roots of polynomial equations. So we got to figure out what a polynomial equation is. And I know we've dealt with polynomials before and factored them and all of that. But now we're going to look at this in general, a polynomial function. And I know this looks like a big mess with all these subscripts and superscripts or exponents there. But it's really just a general way to show any polynomial of any number of terms. So that's what the dot 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 here is, so we don't know how many terms are in between these. And generally, the coefficients can all be different, so they all have different subscripts, right? And you start with the highest exponent, whatever that highest exponent would be, and it should decrease by 1 each time. And sometimes, you know, if say this coefficient is 0, this term is not there, right? So it might look like it decreases by 2 when you get from one term to the next, but it is technically still there. Decreasing until you get all the way down here where x is raised to the 1 power, so it's just x, and then you have the term where x is raised to the 0 power, and it's just equal to 1. Okay, so that's your general, so don't let this freak you out or anything. And then when we talk about a polynomial equation, it's when this whole big mess is equal to 0. And when it's equal to 0, we can actually solve to figure out what x's would make that polynomial equal to 0. Not that we're going to go through and solve this right now, but I'm just saying, as an example, here's our polynomial. You can see that all the coefficients are different. You see the exponents are decreasing by 1 each time, and I have it equal to 0. So in theory, we could solve this and figure out all the x's that would make this true. So our fundamental theorem of algebra says that every polynomial equation that has a degree that's greater than 0 has at least one real or imaginary root. So at least one. Could be more, but at least one. Okay, that's the fundamental theorem of algebra. Anytime anything is a fundamental theorem, you know it's a big deal. But in this case, while this is a big deal, it really doesn't allow us to do a whole lot when we go to try to solve things. So there's actually a better theorem for us to use, and that is called the number of roots theorem. And this one says that if you have a polynomial equation of degree n, that it's going to have exactly n roots. So that means that if you have a quadratic equation, the degree is 2, you're going to get 2 roots. Remember, roots are the same as x-intercepts, so solutions. If it's degree 3, you're going to have 3 roots, okay, and so on and so forth. Well, the roots themselves can be in any form. They could be real, imaginary, rational, irrational. They could be multiple roots, so you can get an equation where the answer is always 3, but it occurs 3 different times. Yeah, so keep that in mind. That's going to be a real powerful thing. So when you're looking at an equation that you're trying to solve, just look at the degree, and you know that that's how many solutions you should be finding. Okay? All right, so if we look at this equation right here, we've done this before with synthetic division. They're telling you that one root is -3, and it says find all the others. So first of all, how many should you find? If we already have 1, how many more are there? And hopefully you can see there's a 3 here, that's the degree, so there should be 3 roots. Well, we've got one of them, so we need 2 more. So how do you get the other ones? Well, we're going to do synthetic division. If you forgot how to do that, take the coefficients of all these terms and line them up. The root, or the solution, goes in this little box over here. And you bring the 2 down below, and then you multiply 2 by this number and put it in this column, and then you add and you continue on and finish off until you get to this last number. And this last number is your remainder. So when the remainder is 0, you know that it's been factored, if you will. And then you can put this back with the variables. So this will be a 2x squared minus 5x plus 2. So with that, if we set that equal to 0, we can now factor it, and we get 1/2 and 2. So all 3 roots for this equation would be -3, 1/2, and 2. All right, so we're going to revisit the complex conjugate theorem. Before, we said that the complex conjugates, when you multiply them together, is the sum of roots. Well, I'm sorry, sum of squares. The second part of the complex conjugate theorem says that if you know a complex number is a root, then you automatically know that its conjugate is also a root. And if you recall, a couple sections ago, we talked about the discriminant, that if you have imaginary roots or no real roots, that you will have two imaginary roots that are complex conjugates of each other. So that's, coming from this theorem here. So when you look at this problem here that you have x to the fourth plus 5x squared plus 4 equal to 0, and I'm telling you that two of the roots are I and negative 2I, find all the others, there's no calculations you have to do. First of all, we know there's 4 roots because the degree is 4. We've been given 2, and the 2 that we were given are imaginary numbers or complex numbers. So we know that the conjugates of both of these are also going to be roots, and there's our 4 roots. So all you have to do is say that the conjugate of I is negative I, the conjugate of negative 2I is positive 2I, therefore negative I and 2I are your roots. Okay, so sometimes it's as simple as that. So if you can use these theorems to your advantage, there's a lot less work that you would have to do. And in fact, if you tried to do synthetic division with this, you'll find that you can't do it because all of the answers or all of the roots are imaginary. All right, so now we get to the next, the rational root theorem. And this looks like a big old mess, doesn't it? Once again, we're looking at our polynomial equation. Okay. I'm going to be looking at the coefficient of your first term, which is a sub 0, and the constant, which is the last term, a sub n. And I'm going to be talking about factors of each of them. So if I'm saying p is a factor of this last term, and q is a factor of the first coefficient, then to figure out all the possible rational roots of this equation, you just take p and divide by q. So take factors of the last term and divide it by factors of the first coefficient. And that gets you your pool of numbers to choose from when you have to do synthetic division. So if you remember, way back before when we did this in chapter 6, we just took factors of this last term as choices to use. And that's because all of our problems had 1 as a coefficient here. So all of these factors divided by 1, those were all your choices. Well, now we might have some other numbers here. So let's see how this works. They give us this equation, this polynomial, that we are asked to find all roots. So the first thing I'm going to do is figure out what the factors are for 2 and 3. So the factors of 2 are plus or minus 1 and plus or minus 2. The factors of 3 are plus or minus 1 and plus or minus 3. So when I am going to build my pool of possible numbers to use for synthetic division, I'm going to do all the combinations of these numbers divided by those numbers. So that's going to give me plus or minus 1, because this divided by 1, plus or minus 1/3, 1 divided by 3, plus or minus 2, which is 2 divided by 1, and then plus or minus 2/3, which is 2 divided by 3. So any of these 8 numbers here are possible rational roots. So you're just going to test them by using synthetic division. And I will tell you, not that I'm going to show it here, but when I tested positive and negative 1, neither of those worked. So I started with 1/3, because that was the next one in my list. And 1/3 actually works. So if we go through and we do the synthetic division, 3 times 1/3 is 1. That turns out to be 0. So that's 0. Add that. 1/3 of negative 6 is negative 2. And then we get 0. So there's our remainder. We did it. Yay. So now what I'm going to do is I'm going to put this back with variables. So 3x squared minus 6 equals 0. Solve for x, and I get plus or minus root 2. So these roots are irrational, and this is the only rational root that we got. Okay, because they're not always going to be rational. So there are my solutions, all 3 roots, 1/3 plus or minus root 2. Okay, that was a big one, huh? But we're done with chapter 9, so that's good. All right, see you later, folks.